Hello, everybody. Welcome back to our channel. I'm Shrutika, having around 13 plus years of experience in various domains and technologies. Have worked with companies like Infi, Accenture, Mindtree, and now I am a freelance trainer on data science. So, in this video, we are going to discuss a kernel and a notebook created by Mr. Prashant Banerjee around 2 years ago, and it is on Kaggle, as you can see here. So actually this notebook gives a very good insight into working with the decision trees for both classification and regression kind of problems. So here we will just discuss some of the theoretical concepts in decision tree in short, and then we will have a look through the code also. Okay, so you would be definitely having some idea about what exactly the decision trees are. So just to give a recap, as the paper itself says, so actually it is one of the most popular machine learning algorithm, and it is a supervised model. Actually, it means that while training we will be having the target feature as well, and only during the testing or in real time predictions we will not be having the target feature, and we will have to predict it using the decision tree algorithms. Okay, so a typical decision tree I will like to show you. uh, just so I will just pause it, and again I want to show you another screen actually. So I hope you are able to see the screen here on the PPT. Okay, so it is a typical decision tree kind of model shown here in the PPT actually. So as you can see, the depth here, the depth of this decision tree is 3, which means that there are actually three levels of segregation done in this decision tree. There will be a root node, and the root node is further divided into child, the next child, and the next child. So as you can see here, there are total of the total depth is 3 here. So um, once we have gone through this diagram, I will just like to go back again to the blog itself, which we will start discussing further. Okay, so now you have an idea how the decision tree looks actually. So it will be having the root node, okay, the initial node, which will actually be having all the data set, the complete data set the root node will be having, and depending on some of the decisions it will be segregated in the form of child nodes. Okay, so a decision tree is a structure that includes a root node, branches, and leaf nodes, and each internal node denotes a test on an attribute. Each branch denotes the outcome of a test, and each leaf node holds a class label. Okay, so if we just go down here, okay, so some of the assumptions uh, we will see the assumptions also. So here actually what the assumptions that they have made is feature values need to be categorical. If the values are continuous, then they are discretized prior to building the model. Okay, so this thing they are planning to do if at all the features are continuous. Okay, and the records are distributed recursively on the basis of attribute values. So now if we go further down, as you can see, the decision trees can be used for both classification well as regression type of problems. It means that if the target is having some fixed classes, then it will be a classification problem. Otherwise, if it can have any kind of continuous values, then it will be a regression problem. So just a short form of classification and regression trees, that is the CART, is generally a modern name that people are using for the decision trees. And actually these decision trees, they form the basis for the um, much more sophisticated models. For example, the back decision trees, the random forest, and the boosted decision trees. So these are actually some more complex and sophisticated models, the basis for which is a normal decision tree, as we are going to discuss it in our video now. Okay, so just going through the terminology, as you know, what is the root node? So it represents the entire population or sample. So this further gets divided into two or more homogeneous sets depending on the decisions, the conditions that we are trying to put. Fine. Then there is a process of splitting while we are making the decision trees. So it is a process of dividing a node into two or more sub nodes, again depending on some decisions. And then decision node, when a sub node splits into further sub nodes, then it is called a decision node. Fine. And what are the leaf or terminal nodes? So the nodes that do not split are called leaf or terminal nodes. So that will be the final nodes which won't be further splitted into their child nodes. And there is some one more terminology which is called the pruning. Okay, and when we remove subnodes of a decision node, this process is called pruning. So if pruning, this is a general English term which we generally use in the agriculture or the plantation kind of systems, where what the agriculturists will generally do, they will remove some of the parts of a tree, a general normal tree, and we will try to remove the parts of the tree so that the results of the tree in normal agriculture system, it will be the fruits or flowers, so that will be of the better quality. So the same terminology we will be using here, pruning. So here what we'll be doing, we will be removing some of the leaves or some of the nodes of a typical decision tree, so as to get the better results of the decision tree. Okay, so in order to discuss this process further, pruning, actually what happens as the depth of the tree keeps on increasing, so slowly the model will start overfitting. So what does this overfitting means is, um, it will be giving good results for the training data because it has learned the training data. But when we are passing the test data, then it will start giving the predictions, will be having more variance from the actual values. Okay, and the accuracy will be less. So ideally, if the accuracy of the test data, the difference between the accuracy of the test data and the trained data is more than 5%, then generally we will say that it is a kind of overfitting that is happening. So in order to remove this kind of overfitting, we will generally try to remove some of the nodes or some of the depth. We will try to limit the depth of the decision tree. Okay, so that is called pruning. Now, there is something called as a branch or a subtree. A subsection of an entire tree is called a branch or subtree. Then parent and child node. A node which is divided into subnodes is called the parent node of subnodes, where subnodes are the children of a parent node. So it is, these are quite from the terminology itself, you will be able to understand what these things exactly mean. So this is a typical diagram that he has shown, giving all the terminologies. Fine. And some of the intuitions behind this decision tree algorithm which he has tried to create in this blog. So these are, for each attribute in the data set, the decision tree algorithm forms a node, the most important attribute is placed at the root node. Okay, so how to find which is the most important attribute, that we will see further in our video. Actually, we have discussed it in some of our past videos also. So here we will be discussing it in further detail. Then for evaluating the task in hand, we start at the root node and we work our way down the tree by following the corresponding node that meets our condition or decision. So these are some typical things which you can go through this block to get further details about. Then now coming to the more important point, that is the attribute selection measures. So this actually we have discussed it in great depth in some of our previous videos, but here also we'll just have a look through these things and then we will move forward. Okay, so the popular techniques that generally we use while creating the decision tree are the information gain and the Gini index. So these terminologies we will be using to identify which feature we should use to create a decision node and um, further split the node into child nodes. Okay, so information gain as we had seen earlier. Okay, so by using information gain as a criteria, we try to estimate the information contained by each attribute. Okay, so to understand the concept of information gain, we need to know another concept called entropy, which we have already discussed in our the previous video, and this was the formula. Okay, summation of minus pi into log 2 pi, where what is pi? Pi is the probability associated with the ith class. Okay, so in this way, we are finding the entropy of data set. Okay, so entropy will be using for the information gain. So what we'll be doing, we will use this formula, okay, to find the entropy of the parent node. And let us say if we are using some feature to segregate and create the child nodes, in that case what will be the summation of the entropy of the child nodes that we will calculate. And if the difference, whichever we will do this process for mostly all of the features which we think they are important, and whichever feature is giving us the highest difference, that we will consider to create the child nodes. To we will use that features to create the decision and further create the child nodes. So in the same way, either we can use information gain or the Gini index. So in similar way, he has shown how to use the Gini index now. So he has used this formula to create the Gini and the Gini index in turn. Okay, so in overfitting in decision tree algorithm, so here he is further discussing it as a pre-pruning and post-pruning. So what exactly these things are, pre-pruning and post-pruning? So the thing is, in pre-pruning, what we will do, we will generally provide the maximum depth of the decision tree that we want. Okay, so before creating the model itself, we will provide that this is the depth. Let us say the depth equal to 3 or 4. So this is the maximum depth that we want for the model. While in post pruning, what we are going to do is we will find the accuracy of the test, and if we find that it is overfitting, then again we will create a model with lesser number of nodes. So that is the post pruning. So any of these two methods can be applied, and obviously this pre pruning, it will take lesser time as compared to post pruning, because post pruning it will be a recursive method where again and again we will be finding the accuracy. If the results are not up to the mark, again we will create a new decision tree with lesser number of depth or the lesser number of child nodes. So definitely post pruning is going to take more time, but at the same time what we are doing is slowly we are, what I can say, slowly we are creating a model where we want to get the exact accuracy that we want. Okay, so post pruning may give us better results as compared to pre pruning, but pre pruning definitely it will take lesser time as compared to the post pruning. Now we will just jump into the code now, because earlier anyway we have seen all these kind of terminologies. So we will go into the code and start analyzing through the code itself. So as you can see here, he has imported some of the libraries, the NumPy library, Pandas, PyPlot, Seaborn. These are all the libraries that he has imported, and then he has imported the data. Fine, from the directly from the Kaggle itself, some car evaluation set he has imported from the Kaggle itself. And then he started, first of all he read the data into the data frame, and then he started exploring through this data. So the generally whatever the exploratory methodologies we use, that is the shape, as you can see the data frame, the shape is 1728 and 7, which means that there are 7 columns and 1728 rows or the observations. So out of these 7 columns, one will be the target feature, and the remaining 6 are going to be the independent features, which will we always be using to predict the target features. Further going down, okay, so some of the few rows we are seeing at this point of time. It is not giving us the column names. Okay, you can see it is just giving us the column numbers. So in order to understand this, from the physical significance point of view, he has renamed the columns. Okay, as you can see, and now we can see exactly what does this value means. So as you saw, it is a kind of car evaluation kind of data set. So buying, it may be the budget buying, which is very high, or these kind of things. Again, maintenance, it is a kind of budget. Then the number of doors, the number of persons, and the it is some another feature that he is using. Safety, which can be low, medium, high, and finally the class. Okay, so class is unaccepted, accepted, good, and very good. As we drill down, we will be seeing. So these are the classes, or the final target values which we have to predict from the remaining 6 of the values. So as you can see here, definitely buying, maintenance, lug boot, and the safety, as well as the class, these are all categorical parameters. But those and person, some numbers we are seeing, so we have to decide whether it is exactly a numerical or an ordinal object. Mm, so if you see car doors, it can't have any infinite number of doors. Maximum 2, 3, 4, 5, at max 6. So there will be some discrete values that the doors can have. Okay, so it means that it is also going to be an ordinal number, ordinal feature. At the same time, persons also, this can't be some in, it can't be any number. A car cannot, the what we can say, the capacity of the car cannot be any infinite number of persons, but here also some discrete values will be there. So apart from the other categorical features, even the door and the person, we can say that they are categorical. Okay, so from depending on the domain, actually this is a very common sense kind of thing, but generally when in the real time projects, so at that time lot of domain information is also required to decide whether a feature that you can see, it might be having numbers, but whether it is really a numerical column or a categorical column. So that is the kind of domain expertise a person should have if they are going to create a model, um, and are expecting a good accuracy out of that. So further, we want to see the number of non-null objects and all these things. So we can see that actually there are 0 null. values, it means that all the observations are complete. We are having the complete observations in the data set. Further down, we are seeing the frequency distribution of values in variables. So as you can see, okay, so first of all, for this buying, you can see that it is normally distributed across all the values. Fine, buying, then further maintenance, then doors, persons, lug boot and safety. Okay, you can see that all the input features, they are all normally distributed, but when it comes to the output class, the target class, here we can see that now this thing, the distribution is a kind of skewed, with the unaccepted having the highest frequency, followed by accepted, then good, and then very good. Okay, so this is the kind of distribution and the data set that we are having with us. Now, if we move down, so this we have already seen, and we have seen that the missing values or the null values, it was already zero. So that is what we are able to see from this statement also. Now, what they are doing is, they have created X and Y features out of the parent data set. So simply they have removed the target feature, and the remaining columns they have taken in another data frame and named it as X, as the general do's and don'ts say. And the target feature they have taken in another variable data frame, that is y. And then they are using the scikit-learn library to create the train and test. So as you can see, the size they want is a ratio of 33%. Okay, so the test size will be 33%, while the remaining whatever is there, it will be the train. And the some random state, random seed they want to use, so that again and again, if you want to run the test, again and again, if we want to run this program, we are able to get exactly the same results which are replicable. So further, after splitting, if we see the x train and the x test shape, we can see that it has been splitted according to the percentage that we had given there. So after this explanatory data analysis, we come back to the feature engineering part. Okay, so this also we have already discussed that the data type is going to be object for everything. Now further going down, because it is an object, the data type is an object, they are trying to encode these features. Okay, so they have used the category encoders library, and they are using the ordinal encoder. So if you can see, they have created an object and they are using fit transform, okay, to train the encoder, and finally they are using the transform on the test, so that X train and X test, everything has been encoded. Now further going down, if you can see, now the values, everything is encoded. Now you can see, as because we have used the ordinal encoder, so you can see the numeric values in place of whatever string values were there. So both in X train and X test, you can see that there the data frame has been completely encoded. Now we will move to the decision tree classifier, and this time we are using the criteria as Gini index. So what exactly he is doing is, one by one he will use the criteria as Gini index, and then he is calculating the overall accuracy given by the decision tree. Again, he will be using the criteria as information gain, and again he will try to see what is the accuracy. So if we go further down, you see there from the scikit-learn tree library, they are importing the decision tree classifier, and they are creating the object decision tree classifier object. They have created, and the criteria they have used this time, it is the Gini. And if you can see, maximum depth is 3, it means it is a pre-pruning. Okay, before the model is created itself, we have fixed the depth as 3 only. And then after creating the object, they are trying to fit the model by providing both the X train as well as the Y train. So if we come down here, okay, once the model has been created, then they have used the predict method to predict the target features for the for the test data set. So from this, see, we here for the test data set, we are finding the predictions and we are having the actual values also. Okay, so we are finding the accuracy score. So this accuracy score, this method is giving us the accuracy, which is 0.8021. Okay, so this is the model accuracy score which we got using the criteria as Gini index. Okay. Now, if we want to compare the accuracy that we got from the trained set as well as the test set, so again, see what they are doing is they are using the same model, and this time they are trying to predict the values for the training data. Okay, so we got the predictions for the training data. We have the actuals for the training data, and using the predictions and the actual, they are trying to find the accuracy score. And as you can see, for the training, we got the training set accuracy score as 0.7865. Okay, so ideally speaking, there is no overfitting at all. Okay, but we can say that yes, there might be a little bit of underfitting, we can say, because the training set accuracy score is lesser than the test set accuracy score. So no overfitting definitely, but yes, there are chances that there is a kind of underfit and the model can be improved. So further going down, they are checking for overfitting and underfitting. And why they are saying that there is definitely, they are saying that there is no sign of overfitting, but they are not saying anything about underfitting here actually. But from our observations, it seems that because training accuracy is lesser than test set, so it can be further improved, and that is what our point of view says about this thing. So now what they are doing is this decision tree that they have created, they want to plot the decision tree to see exactly how they are using the various decisions to split the tree down. Okay, so if we see here, okay, so now x5 is less than equal to 1.5. So if we just see what is the x5 feature, mm, okay, so 0, 1, 2, 3, 4, 5. So it is safety. So safety feature they are using, and then okay, so if safety is less than equal to 1.5, this is the decision that they are using to split down the data set into further child nodes. Okay, and then in this case, okay, here in the root node, we are having the complete data set, and they found that Gini for this thing was 0.455. Okay, the total samples are 1157, that is the number of observations. And the value, this is giving the overall frequency distribution um, for the target data set. Okay, and then if we use this decision, we find that one node we are getting where the Gini is 0.0, and as you can see, frequency distribution. Okay, so we are getting only one class here, so which is perfectly split actually. So all the data set, all the rows which are coming to this node, so they will be having the classes 386. Okay, so the total samples is also 386, and the class frequency distribution is also 386, because all the other classes the frequency is 0, as you can see here. Okay, this is the left node. But if you come to the right node, again you can see that the Gini is 0.55. So first of all, if we see what is the difference, okay, here the Gini is 0.455, and here if we see 0.577 plus 0.0, so 0.577 minus 0.455, so we can say the Gini difference is coming as 0.122. That is what it is coming. And so definitely Gini for children, Gini for child nodes is more than the Gini for the parent. That is why decision tree they have used. This decision they have used in this tree. Okay, and then further the samples here are 771, and the frequency distribution is something like this. So you can go through some other videos also, which will give you how to read this decision tree, overall how to read this decision tree. But the in brief I have explained you. So now for the second child, they will be using x3, so maybe the number of persons whatever is there on the third column, exactly they will be using that decision to further split it down, and in this way it has happened. So they have created the model that they have used, actually they have plotted this model. And the same thing they have done using some another graph, some another library which is giving a better graph. And as you can see here, they are using some kind of color codes. So wherever the Gini is 0.0, okay, which is like the perfect distribution is happening, the perfect split has happened. So there you can see some darker shades of blue are there. So here in this box, then in this box also you can see some darker shades of blue are there. Okay, now the same thing they are repeating using the criteria as entropy. So here you can see the same model they have created. Okay, so the same object they have created, and this time the criteria that they have used is the entropy. Again, maximum depth they have given is 3. So, and then they are for this fitting the model for the training data set. And then they are predicting the values for the test data set using the predict um, function. So the exactly the same process they are using. Again, if you can see, the model accuracy for the test is 0.8021, and the model accuracy for the train they are finding is 0.7865, which are the exactly the same values which you got earlier using the Gini index. And again, they are getting the same results for overfitting and underfitting also. Now again, if we visualize the decision tree, see exactly same decision tree has been created here also. Okay, see exactly the same safety. They are using the safety feature, then they are using the persons feature. So exactly it is being created, and then they are finding the confusion matrix. Okay, because it is a kind of classification type of problem. So we are using the confusion matrix. And just to reiterate, the confusion matrix will be using the true positives, true negatives. So what exactly these are? True positives occur when we predict an observation belonging to a certain class and the observation actually belongs to that class. Okay, then true negative occurs when we predict an observation does not belong to a certain class and the observation actually does not belong to that class. Okay, then what is false positive occurs when we predict an observation belongs to a certain class, but the observation actually does not belong to that class. So you can just go through these things because earlier also we have studied these things in our videos. and then they tried creating the confusion matrix. So see, for as you can see, there were four classes: unaccepted, accepted, good, and very good, I think. So for that, it is giving the complete decision tree. So it is a kind of 4 by 4 matrix that you can see here. Now further going down, they have created the classification report also. Okay, so you can see the precision, the recall, F1 score, support, everything. So if you just want to recollect what these things are, so precision is the ratio of correctly predicted positive observations to the total predicted positive observations. Okay, so if you can see here, for the unaccepted, okay, the precision is more. At the same time, the recall is also more. Recall is the ratio of correctly predicted positive observations to the all observations in the actual class. Okay, so for you can see, because the precision and recall both are more for unaccepted, the F1 score is also coming to be more. So F1 score, we can understand it is a kind of accuracy only in a more sophisticated and complex way. So generally, F1 score will be using if the distribution of the target column is not, it is, if it is not normally distributed, then we will be considering F1 score instead of the accuracy. And you can see that for the unaccepted in this class, these values are all higher. It means that if there is a let us say some observation for which we want to predict, and if this model, this specific model, if it predicts the value as unaccepted, then we can be more confident for it to be correct, because as we can see, the F1 score is higher for this class as unaccepted. And further going down, for accepted, the values are 0.56, 0.57 and all. And if you see for good and very good, it is completely zero. Okay, the model is giving the values as zero. It means that we can never ever be confident if first of all the model is not predicting any values as good or very good, and if at all it predicts, then we can't be confident enough that this value is going to be correct. Why so much of skewedness is there is because this thing, the target class, it is not normally distributed. We had seen that most of the values were within unaccepted and accepted, and very few were in good and very good. So this kind of skewness has been created because there is no normal distribution for the class, for the target class. So they are finding the results and conclusions. So I will just go through it, and if at all there is some explanation, I will explain it in my own language. So in this project, the person has built a decision tree classifier to predict the safety of the car, and two models they have built, one using Gini index and the other using criteria entropy. And for both of the models, they are giving exactly the same accuracy for the test as well as the train. Then the training set accuracy, as we have seen, these are 0.78 and 0.80, which are quite comparable, and that is the reason that the author, he is quite happy with the results. So actually, every time depending on the use cases, and so there is some threshold level which is required. So depending on this domain, the author is quite happy with the threshold that has been achieved. Then similarly, in the model with criteria entropy, they are getting the exactly the same results. And then the confusion matrix and the classification report yields very good model performances. So that is what the author is very happy about. So this was all about the decision tree. We went through the blog, and we have seen how exactly he has used um, programmatically, how he has used various features and functions to create the decision tree. I hope this video is quite helpful to you, and further you people can go through this blog to understand these things further in more detail and depth. So thank you so much for watching this video. Bye for now.